Look up. The night sky is a velvet canvas dotted with diamonds of distant light. Each star is a sun, a world of fire and fury, yet from here they appear serene, fixed, and impossibly far away. There is a profound paradox in this view. We see a universe of immense scale, a cosmic ocean stretching for billions of light years in every direction, and yet we are bound to this one small blue marble. The stars whisper an invitation, a call to explore, but the distances are so vast that they seem to mock our ambition. A journey to even the nearest star, Proxima Centauri, would take our fastest current spacecraft tens of thousands of years. It feels like a cosmic joke, a universe of wonders, forever beyond our grasp. This separation has fueled human imagination for centuries. Stories of gods who could cross the heavens in an instant. Myths built around the celestial bodies we could only observe, filled with faster-than-light drives and cosmic portals. Among these ideas, one grips our collective psyche, the wormhole, a concept that feels like magic, a secret doorway hidden in the fabric of reality. It promises to bend the rules of space itself, to turn an impossible journey into a single step. But the idea is not just fantasy. It doesn't originate in a storyteller's mind, but in Einstein's equations. General relativity. Science and wonder collide. The same theory that describes the orbits of planets, the bending of starlight, the existence of black holes, also contains mathematical solutions for shortcuts through spacetime. They are not proven to exist, not yet. We have never seen one. Still, the laws of physics allow for their possibility. A tantalizing clue that the universe might be stranger and more interconnected than we imagine. So we stand on our planet looking up, caught between limitation and possibility. The universe appears static and impassable, isolated islands of light. But what if it's not? What if the fabric of space is folded in ways we cannot see? What if there are hidden tunnels? Cosmic subways that connect distant shores of the galaxy. This is the grand puzzle of the wormhole. It challenges assumptions about distance and about time. It invites an intellectual journey to explore reality itself. A journey that begins not with a spaceship, but with a simple piece of paper. To understand a wormhole, we must first reconsider what we mean by space. For most of human history, we thought of space as an empty, unchanging void. It was a passive backdrop, a cosmic stage upon which the drama of planets and stars unfolded. But Einstein's revolutionary insight was that space is not a stage. It is an active participant in the cosmic dance. He conceived of space and time as being woven into a single four-dimensional continuum, spacetime. Imagine this spacetime as a vast, flexible fabric, like a stretched rubber sheet. It is the very substance of the universe, and it can be bent, warped, curved by the presence of matter and energy. This is the essence of gravity. It is not a mysterious force pulling objects together, as Newton envisioned. Instead, gravity is the curvature of spacetime. Place a heavy object, like a bowling ball, onto our rubber sheet. The sheet dips and sags around the ball. Now, roll a smaller marble nearby. The marble doesn't get pulled toward the bowling ball, it simply follows the curve in the fabric created by the ball's mass. This is how planets orbit the sun. The sun creates a deep well in the fabric of spacetime. Earth rolls along the edge of that well, caught in a perpetual orbit. Every object with mass creates its own indentation in this cosmic fabric. Now, let's take this analogy a step further. Imagine an object so incredibly dense and massive that its gravity is overwhelmingly strong. Imagine a star collapsing under its own weight until all its matter is crushed into an infinitely small point. A singularity. This object creates an incredibly deep, steep well in the fabric of spacetime. So deep that nothing, not even light, can climb out. This is a black hole. A one-way door in the universe. A point of no return. The edge of that point of no return is the event horizon. It's the boundary where escape velocity exceeds the speed of light. Black holes are the most extreme warping of space-time we know of. They are places where physics breaks down at the center. They show the fabric of the cosmos can be twisted and even punctured. From this extreme curvature, the idea of a wormhole emerges. If a black hole is a deep well or a funnel in the fabric of space, a wormhole is more radical. A tunnel connecting one part of the fabric to another, potentially linking two vastly distant points via a shortcut. The first theoretical glimpse of a wormhole came shortly after Einstein published his theory of general relativity. In 1935, Einstein, Nathan-Rosen, were exploring the bizarre mathematics of black holes. They were trying to make sense of the singularity, the point of infinite density at a black hole's center. In their mathematical model, they found a curious solution. Instead of a single funnel leading to a dead end, their equations described two funnels connected at their narrowest points. It was as if the fabric of space-time could be pinched together to form a bridge, a tunnel connecting one region of the universe to another, or even connecting our universe to another, separate one. This theoretical structure became known as the Einstein-Rosen bridge. Let's return to our simple analogy of a sheet of paper. Imagine two dots drawn on opposite ends of the sheet. First dot, second dot. To get from one dot to the other, you would have to travel the entire length of the paper. That's the long way. But what if you could fold the paper in half, bringing the two dots very close to each other in three-dimensional space? Now, if you could poke a pencil through the paper at both dots, the pencil would form a short, direct tunnel between them. This is precisely the concept of an Einstein-Rosen bridge. It's a shortcut not across space, but through a higher dimension that folds our familiar three-dimensional space. In this model, the entrance to the wormhole would look very much like a black hole. An unsuspecting traveler approaching it would feel an immense gravitational pull and see the space-time around them becoming increasingly warped. The throat of the wormhole is the narrow channel that connects the two mouths. In theory, one could enter the mouth of the wormhole, travel through the short throat, and emerge from the other mouth in a completely different part of the cosmos, potentially millions of light years away, in what would feel like a very short amount of time. It is the ultimate cosmic shortcut, a way to cheat the vast distances of the universe. However, the original Einstein-Rosen bridge came with a significant catch, a fatal flaw that made it useless for travel. According to the mathematics, these bridges are incredibly unstable. They would pinch off and collapse into a singularity the moment they formed, or the moment anything tried to pass through them. The throat of the wormhole would slam shut faster than the speed of light, meaning not even a single photon could make it through. So, while Einstein and Rosen had discovered a beautiful mathematical possibility, their bridge was a one-way ticket to oblivion, not a traversable highway between the stars. It was a fascinating dead end. The dream of traveling through a wormhole seemed to die with the discovery of the Einstein-Rosen bridge's instability. A bridge that collapses the instant you step on it is not a bridge at all. For a wormhole to be useful for travel, it needs to be traversable. This means two things: throat big enough for a person or spacecraft to pass, remain open long enough for the journey. The challenge became, what could prop open the throat against immense gravity? The answer feels like science fiction. In the 1980s, Kip Thorne and others proposed a solution: exotic matter. Not just rare or strange matter like antimatter or dark matter. Exotic matter has a bizarre property: negative energy density or negative pressure. Think about normal matter and energy, the mass of a planet, the light from a star. Normal matter has positive energy. Einstein's equations say that positive energy makes space-time curve inward, gravity. It's what makes the rubber sheet sag. Exotic matter does the opposite. Its negative energy would push space-time outward. It would act anti-gravitational. Placed in a wormhole throat, exotic matter could act as a cosmic scaffold, holding the tunnel open, like inflating a balloon inside a collapsing tube to stop it pinching shut. That material would need incredible strength, exerting tremendous outward pressure to counteract gravity in the throat. But we've never observed a lump of exotic matter. We don't know if it can exist in the quantities needed for a macroscopic wormhole. There are microscopic hints in quantum physics, notably the Casimir effect, where tiny negative energy appears between two closely spaced metal plates. But it's extremely small and localized. Scaling that up to hold a spaceship-sized tunnel is a monumental technological and physical challenge. Without a source of anti-gravitational material, traversable wormholes remain theoretical, beautiful equations with no known physical ingredients. Assuming for a moment that we could find or create enough exotic matter, what would a journey through a traversable wormhole actually be like? Well, this is where theoretical physics allows us to become explorers of the imagination. Mapping out a voyage through a structure that may or may not exist. A traversable wormhole would be fundamentally different from its unstable cousin, the Einstein-Rosen bridge. Instead of leading to a crushing singularity, its interior would be a smooth, continuous tunnel through spacetime. The mouths of the wormhole could be located anywhere in the universe, separated by billions of light years. Yet the tunnel connecting them might only be a few meters long, or kilometers long. From the outside, a wormhole mouth might not be as dramatic as a black hole. A black hole is defined by its event horizon, a surface of no return. A traversable wormhole, by necessity, cannot have an event horizon, because anything that goes in must be able to come out. Instead, it might appear as a strange, shimmering sphere, a kind of crystal ball, reflecting a distorted view of the space on the other side. As you approached one mouth, you might see the stars and galaxies from the distant region around the other mouth, their light having traveled through the throat. It would be a window into another part of the cosmos. The journey through the throat would be a strange one. The laws of physics inside the wormhole would still apply, but the geometry of space would be unlike anything we have ever experienced. You wouldn't be traveling faster than light. Rather, you would be taking a shortcut where the distance itself is radically shortened. To an outside observer watching your ship, it would seem as though you approached the wormhole mouth, vanished, and then almost instantly reappeared at the other mouth light years away. For the traveler inside the ship, the journey through the throat might only take a few minutes, or hours depending on its length, all while obeying the local speed limit of light. However, the very existence of such a pathway raises profound questions. What would it take to create one? Some theories suggest an incredibly advanced civilization might manipulate spacetime on a grand scale, perhaps by harvesting exotic matter and carefully constructing a wormhole. Other theories speculate microscopic wormholes might have formed naturally in the chaotic, high-energy early universe, and that an advanced civilization might be able to find one and enlarge it. In either case, the engineering and energy requirements are staggering, far beyond anything humanity can currently conceive of. The traversable wormhole remains a beautiful but distant possibility. Even if a stable, traversable wormhole could exist, and even if we could find one, sending a person through it would be fraught with extreme danger. The environment inside and around a wormhole would likely be one of the most hostile in the universe. The very properties that make a wormhole a shortcut also create a series of deadly hazards for any would-be traveler. The first and most immediate danger comes from the intense radiation that would likely be focused and amplified by the wormhole's strange geometry. Light entering one mouth could get trapped. Other radiation entering one mouth could get trapped, bouncing back and forth within the throat. This trapped energy could build up over time, creating a feedback loop that would blue-shift the radiation to incredibly high frequencies and intensities. Any traveler attempting to pass through would be instantly bombarded with a lethal storm of high-energy gamma rays, other particles. It would be like trying to walk through the core of a star. Even if the wormhole were freshly created and cleared of radiation, the simple act of trying to pass through it might trigger this feedback instability. The traveler's own ship, even the traveler themselves, would introduce energy potentially frying them and causing the wormhole to collapse. Another significant peril is the extreme tidal forces. Tidal forces are the same gravitational effects that cause the ocean tides on Earth. They arise because the pull of gravity is stronger on the side of an object closer to the source of gravity than on the side farther away. Near a massive object like a black hole, these forces are so strong they can stretch objects apart, a process colorfully known as spaghettification. While a traversable wormhole would need to be designed to minimize these forces to survivable levels, the exotic matter required to hold it open would itself create bizarre gravitational gradients. The implications of wormholes extend beyond just conquering space. They twist into the very fabric of time. According to Einstein's theory of relativity, time is not absolute. It is relative to the observer's motion and to their position within a gravitational field. This effect, known as time dilation, means a clock moving at high speed, or a clock in a strong gravitational field, will tick slower than a stationary clock far from any mass. For example, clocks on GPS satellites must be constantly adjusted because time runs slightly faster for them in orbit than for us on Earth's surface. This link between space, gravity, and time has a profound consequence for wormholes. Imagine a traversable wormhole with two mouths. Mouth A, mouth B, initially next to A in a lab. You take mouth B on a spaceship that travels near the speed of light for a year and returns. Due to time dilation, less time passes for mouth B than for mouth A. Suppose mouth A ages 10 years. Mouth B ages only 1 year. The wormhole then connects 2035 at mouth A to 2026 at mouth B. You've created not just a shortcut in space, but a gateway into the past. This opens a Pandora's box of logical paradoxes. The most famous is the grandfather paradox. What if you travel back and prevent your own grandparents from meeting? If they never meet, you are never born. If you're never born, you couldn't have traveled back to stop them. That's a logical contradiction that violates causality, an effect before its cause. The universe seems to enforce strict cause and effect. Many physicists think nature prevents such paradoxes. One proposal, the Novikov self-consistency principle, says any action in the past was already part of history, so true paradoxes can't occur. You might go back to stop your grandparents, but you'd end up causing them to meet. Essentially, you can't change the past because you were always part of it. Wormholes don't just challenge engineering. They challenge our understanding of logic, free will, and the nature of time itself. With all this fascinating and complex theory, the ultimate question remains: are wormholes real? Do these cosmic shortcuts actually exist out there in the universe? The simple and direct answer is that we do not know. To date, we have found no direct observational evidence for the existence of a macroscopic wormhole. Our telescopes have not captured an image of a strange, spherical lens in space. Our instruments have not detected the unique gravitational signatures that a wormhole mouth might produce. They remain, for now, a purely mathematical possibility allowed by our theories of gravity. So, how would astronomers even begin to look for one? A wormhole mouth would be a very strange object. Unlike a black hole, it would not have an event horizon. It wouldn't necessarily be dark. It might be possible to detect one through a phenomenon called gravitational lensing. Just as a massive galaxy can bend the light from objects behind it, a wormhole mouth would also warp spacetime and distort the light of distant stars. However, its lensing signature would be unique. A normal object produces a positive lensing effect, pulling light inward. The exotic matter of a wormhole mouth might produce a negative outward lensing effect. Stars behind it could appear to fly away, a truly bizarre sight. Another potential signature could come from interactions of stars with a wormhole mouth. If a star passed in front of a wormhole, its light might be briefly and strangely magnified. If a star were in a stable orbit around a wormhole mouth, it would behave differently than an orbit around a normal star or around a black hole. Astronomers are constantly scanning the skies for such anomalies. The discovery of an object with negative mass, or one that exhibits the unique gravitational signature of a wormhole, would be one of the most profound discoveries in the history of science. in recent years, a more subtle and theoretical connection has emerged. Some physicists are exploring a deep link between wormholes and quantum entanglement. Spooky action at a distance. The ER-CAS-EPR conjecture proposes that two entangled particles might be connected by a microscopic, non-traversable wormhole. It's a frontier idea attempting to unite quantum mechanics and general relativity. While this doesn't offer a pathway to the stars, it suggests spacetime might be woven from quantum connections. The universe could be interconnected in ways we are only beginning to comprehend. The search continues in the sky, and in the very equations that describe reality. We began with a paradox, a universe of wonders that seems forever out of reach. The wormhole presents a theoretical solution, a bridge across the impossible void. We have journeyed through the science, the flexible fabric of spacetime, the unstable Einstein-Rosen bridge, the idea of a traversable tunnel held open by exotic matter. We have confronted the immense challenges, lethal radiation, crushing tidal forces, bewildering paradoxes of time travel. The scientific consensus is clear. We have no proof that large, traversable wormholes exist. They are an elegant but unproven consequence of our best theory of gravity. Yet the idea of the wormhole endures. It holds a power that transcends the dry equations. It speaks to a fundamental human desire, the desire to explore, the desire to connect, the desire to overcome our limitations. For millennia, we have been explorers. We crossed oceans, we climbed mountains, we stepped onto another world in our own solar system. The dream of interstellar travel is the next logical step in that grand human adventure. The wormhole represents the ultimate hope, a loophole, a secret passage that makes this dream possible. It transforms the universe from a vast, lonely expanse into a potentially interconnected neighborhood. The study of wormholes, even if they turn out to be impossible, is an incredibly valuable endeavor. It pushes the boundaries of our knowledge. It forces us to ask deep questions about the nature of space, time, energy, information. It shines a light on the gaps in our understanding, particularly at the intersection of gravity and quantum mechanics. The quest to understand if a wormhole could exist is also a quest to find a complete theory of the universe. Every calculation, every thought experiment brings us a little closer to understanding the fundamental rules that govern our reality. The journey is as important as the destination. And so, we are left where we started, looking up at the night sky, but now with a different perspective. We see not just distant lights, but theoretical possibilities. We see not just impassable distances, but a cosmic fabric that might be folded and tunneled in ways we can barely imagine. The science is hard, and the challenges are immense, but the wonder remains. The search for answers continues, fueled by the same curiosity that first led us to map the stars. The universe keeps its secrets well, but it has not told us that this dream is impossible. And so we ask, if a shortcut through space and time really does wait for us in the dark, what will it teach us about the universe, and what will it teach us about ourselves? Soft breath.